Rich is well, I was going to say statistician by training. He's a mathematician as an undergraduate, and he did his PhD in statistics with Simon Tavare at Cambridge. Together they developed this approach to Bayesian inference called ABC, which he's presumably going to introduce, so I won't tell you too many details about. But I think it's one of the funkiest things to come out of statistics. In particular, it didn't come out of statistics because they couldn't get it published in the statistics journal. It went in, what was it,
Genetics.
A genetics journal. Yeah. And it's really blown an area wide open with these ABC techniques, and Rich was really at the heart of it. I'm particularly pleased to welcome Rich because he says the University of Nottingham on his slide, but as of 2 weeks ago, he's moved to the University of Sheffield and our stats department here, and Rich is going to be working with me and Mike Croucher and others on a new open data science initiative. So it's his first talk that, well, I've seen you talk from Sheffield before, but when you were a postdoc. And so if we could just welcome Rich, who's going to tell us about BBC and history, Matthew and G, please.
Thank you. So I've just come from the physics department where I've just given an hour's talk. So if I start falling asleep during the middle of it, someone prod me. Okay. So I heard Henry Wynne say once that in order to become an expert in some topic, the best thing to do is just to jump right in and start giving talks about it. So on that basis, essentially what I'm going to do today. So every year Neil invites me to come here and give a talk, and every year I never quite end up talking about what I'm supposed to talk about or what I said I was going to talk about. It's true today. I was listening to the other talks earlier in the week and I was thinking, no one's really mentioned design yet. I know, let's mention a bit more on design, okay? So that links in with what I was going to talk about, which is this, and then we'll get to that. I wanted to just put a bit more review material at the start about design for these things, okay? So what I'm interested in is the analysis of computer experiments, okay, so computer simulators. So if you're a climate scientist, okay, you're going to make predictions. If your climate simulator takes a month to run, in fact, even if it takes 5 seconds to run, it rules out most Monte Carlo type of things you want to do, unless you're going to wait a very long time. And how do we think that make up uncertainty statements, combining model data? So what does this have to do with Gaussian Process Summer School? Well, one of the key kind of methodologies that's been developed over the past 2 decades is around the use of Gaussian processes for doing these things. Okay. So I'll introduce this idea of a Gaussian process emulator, which is a model of your simulator, if you like. So it's a model of your model. Okay. So these are the kind of questions that we want to answer in UQ, in uncertainty quantification. So first one is calibration. I mentioned this already. Okay. How do we estimate parameters, unknown parameters? It's going to be theta here. So typically, that's how do we find the posterior distribution. Yeah? So we've got some data, we've got a prior for theta. How do we do the Bayesian updating to find a posterior distribution? And that's primarily what I'm going to talk about. How do we do that? Okay. Okay? Or sometimes there's a version of calibration called history matching, where you're not trying to find a distribution here, you're just trying to find good parameters and bad parameters. Yeah, so how do we do that? We're going to say these parameters are bad, these ones are good. This is what they do in the oil industry. Yeah? They don't care about distributions, just good or bad. It's like a uniform distribution instead. Uncertainty analysis. If X has got some distribution and f of X is your simulator, what's the distribution of f of X? Okay? If you can't do Monte Carlo, if you can't run your simulator 1,000 times, you can't do it by brute force, what can we do instead? Yeah? Sensitivity analysis. Okay? You've got some complex simulator that takes a bunch of inputs. The output has some variance. Can we decompose that output variance into variance in the different inputs? Okay, we're uncertain about those inputs. And that would tell us things like, if I can only measure one thing, which one of these inputs should I measure to make the biggest improvement in my knowledge? Okay. So, one of the key tools, as I mentioned, is this idea of emulation or surrogate modeling or metamodeling, it's sometimes called. And this revolves heavily around the use of Gaussian processes. Okay. As I said already, if your simulator takes a long time to run, and long can be a second or it could be 6 months, okay, you're not going to be able to do brute force approaches to most statistical analyses you want to do. So what we're left with instead is what's called an ensemble of simulator runs. Okay. So we have a small finite collection of simulator runs. So we have a pairs of inputs and outputs of the simulator. So theta is your input, f of theta is your simulator run at theta. Okay. And you maybe have just a few hundred or a few thousand or a few tens of simulator evaluations. And you're going to have to say everything you want to say about the simulator on the basis of this finite ensemble. Okay. So what can we do in this case? So this is something called code uncertainty. It's called code uncertainty because if theta is a new input, not in this ensemble, not in your design, okay, then you're uncertain about the value of f of theta. Okay. So what we're going to try and do is build a model to predict f of theta. Okay, so this is the idea of metamodeling or emulation. It's a model of your model, or a model of the scientist's simulators. Okay. So the scientists build these complex mechanistic models based on physics. We're going to build simple statistical models of their physical models. Okay, it gets more fun. Okay. So Gaussian processes are great for this because they, as you know, are good interpolators. They're functional regression tools, non-parametric functional regression. Okay? And they're also good for uncertainty quantification because they come with assessment of their accuracy. Yep. You don't just predict the mean when you do a Gaussian process prediction, you also predict the variance as well. Yep. So it's useful in that sense in that we can quantify uncertainties at the same time. Okay, so this is a picture you've probably seen a million times. We start off with some kind of prior specification of functions. This is a one-day example, just a single theta, single output. Okay, some covariance function, some mean, prime mean structure. Okay, we run the simulator 4 times in this case. Okay, so we've got 4 x, y pairs or theta, y pairs. Okay, and then we're going to fit our Gaussian process model, and this is our emulator. So our emulator is this solid line. This kind of tells us our best guess, the posterior mean about what the simulator is doing, and then we've got uncertainty about it. Okay. So you can imagine the directions the kind of field takes from there. You can scale this up to sparse things or high-dimensional things and all kinds of things that you've heard about this week. And we've got lots of interesting examples of that, but not particularly what I want to talk about today. So what are the challenges for UQ? Well, what I am going to talk about is this design problem. Okay? If we can only afford n simulator runs, yeah, what are the best n I could do? Yeah, where should I run the simulator? So this, machine learning, often you're dealing with observational data. You have no choice about where to collect your data from. Okay, you're just given someone's Twitter feed, all this Twitter information, or whatever it is, whatever data you're looking at, you're just given it. It's an observational study. Okay? But computer experiments, and in other types of experiments, we can often design our studies. We can decide where we're going to collect our data. Okay? So if we can decide where to collect it, where should we collect it from? Other questions are how do we deal with high dimension? So dealing with high dimensional inputs is very different to dealing with high dimensional outputs, and there's lots of tools for doing that. Okay. So just a couple of examples of the kind of area that we've been looking at. One is in carbon capture and storage in this transport problem. Okay. So the aim of carbon capture and storage is you're burning fossil fuels in your power station, pumping out CO2. Okay? The idea is to capture the CO2 in the power station and bury it underground, perhaps in the oil well. Yep? So you're going to bury it back where the oil came from. And part of this involves transporting oil and these and carbon dioxide in these long pipes, okay, to where it's being stored. And we need to know the properties of the fluid as it's being stored. Okay? So chemists and physicists have long looked at pressure-volume relationships in gases, but they look at it for ideal gases or very pure gases, for just pure CO2 or pure oxygen. Okay? And it turns out that as soon as you have impurities in, it breaks down. All these models are no longer very good. We don't have very good measurements. We have very limited measurements about how the gas is going to behave. Okay? So essentially we're looking for non-parametric models to model all these different curves to help us predict the flow of the gases. Okay. So we've had great success here with Gaussian processes. And the interesting thing from a Gaussian process point of view is that we need to incorporate types of physical behavior. So one thing is what I call fugacity constraints here, but that basically means that all these curves must integrate to zero between here and here, essentially, at some point. So we've got these Gaussian process models that we guarantee have an integral of 0. Okay. We also guarantee something about their integral derivatives in places. Okay. And we also want to guarantee something about that asymptotic behavior. Okay? We know down here it's the ideal gas law, and here is some other power law. Okay? So these Gaussian process models are very nice because we can incorporate all these different types of physical behavior as well as the empirical behavior that we see from these measurements. Okay, that's one type of computer experiment. Another type is the storage problem. Okay, once we've buried this gas, what are we going to do? Is it going to leak? Where's the gas going to go in the oil well? Is it going to leak out? So again, scientists have very good models here. So they have models of fluid flow in a porous media. Yeah? And all these models take as an input the permeability field. So this tells us about how permeable the rock is where the gases are stored. Okay? And if they know this permeability field, they can predict where the fluid is going to go, so the concentration functions and stream functions. Okay? But of course, this is highly uncertain. They don't know the permeability anywhere, so they want to account for the uncertainty in the permeabilities. You know, it costs £1 million for every well, so they only have about 6 measurements of permeability. And so they want to say, given our lack of knowledge, what's our best guess about where the fluid's going to go, the CO2 is going to go, and is it going to leak? And again, we could do really quite surprising things with Gaussian processes here. So taking this 2D spatial field as an input, so that's 1 million numbers here as our input. Okay? We're going to predict these spatial field outputs. And it's surprising how easy it is to do this in certain situations. So with just 118 training runs here, we're able to reproduce very accurately the kind of spatial fields they see in their simulator and the emulator. So this is truth. This is estimated. Okay? So again, just because it's a high-dimensional problem, just because it's very high-dimensional inputs and very high-dimensional outputs, doesn't mean we can't use Gaussian processes if we combine them with some kind of dimension reduction tool like PCA or GPLVM or something like this. Okay, so the topic I actually wanted to talk about design. So we all know we build Gaussian processes with XY pairs of data. Yep. We've got inputs and output pairs. Yep. And the collection of inputs is called the experimental design or design. Okay. This is some subset of RD. And as I say, for observational studies, we can't control the design. But for computer experiments, we can choose exactly where we're going to run our simulator. Okay. So where should we do the simulation in order to make the best predictions? And the type of design we use is very important. It has a very big effect on the accuracy of our predictions. Okay? Using a good design always gives us better predictions than using a poor design. Yep. So it's worth spending a bit of time before you go away and do your simulator runs to think about what we do here. Also, before we think of a design, it's very important to think what we're designing for. So we've seen two Bayesian optimization talks today. Okay? So if you're designing for optimization, we've seen these acquisition rules. So things like minimizing the expected improvement works well as a sequential rule for doing the design. Okay? But you do something very different if what you want is a global prediction tool for predicting your simulator across all the space. And similarly, if you're doing calibration, you'll do a very different type of design if what you want to do is calibrate your simulator. So the classical type of design that gets used by default are these space-filling designs, these max-min Latin hypercube designs. Yeah? So do you all know what Latin hypercubes are? They are, you know what a Latin square is, basically. If you've got some square, we're going to split it into rows and columns, okay? And you never want a point to be in the same row, okay? Or the same column. Yep. So a Latin square is something where there's no 2 points in any one row or any one column. Okay? A Latin hypercube is the same thing in higher dimensions. Okay? And so these are good because they are what are called space-filling designs. They push the points out and fill space. And that's good for Gaussian process prediction because your variance grows as a function of the distance between points. When you're doing a large interpolation, when you're a long way from the data, your uncertainty is bigger than when you're very close to the data. Okay? So the classical thing are the Latin hypercubes. Okay. And they're very good. They're kind of optimal, or close to being optimal, if you know your hyperparameters already. Yep. But if you also want to estimate hyperparameters, length scales, and so on, okay, then there's a different type of design that's more optimal. If you only cared about length scales, okay, hyperparameters, then a good thing might be a kind of a de-optimal design. So something like maximizing the determinant of the Fisher information matrix. Yeah? So kind of classical statistical theory. Because normally what we want to do is this empirical kriging, or whatever you want to call it, okay? We want to estimate the parameters and make predictions, fit our Gaussian process and predict well. So what people like Michael Stein have shown is that we want a design that a trade-off between being space-filling and between maximizing the Fisher information. Okay. So we get these designs that look like this, where you have points that are spread out in space, but I don't know if you can see, you've got lots of points, pairs of points that are close together as well. Yep. So often if you want to do both estimate parameters and make good predictions, it's useful to have some points that are close together, but generally being spread out. Okay? And that will allow you to do both estimate parameters and make good predictions. So, in a sense, a more interesting question is this question of sequential design. Suppose we're going to build up our design one point at a time. Yep. So like we do in the global optimization things. We're going to run the simulator, our black box once, fit our Gaussian process, do it again. Okay. So those other designs I talked about before are all one-shot designs. It can be wasteful because you learn information from doing a number of runs that you could use to guide later design points. Okay. So by doing it one point at a time, adding points one point at a time, we can hopefully get superior designs. So all these designs work by adding some new design point, by minimizing or maximizing some criteria that depends upon your current Gaussian process fit. So if we currently have n data points, okay, we're going to choose our next data point to maximize some criteria. Okay. And the criteria we use is going to change depending upon what the situation is we're in. Yep. So for optimization, we've seen this expected improvement criterion as a good choice, this EI thing that Javier talked about this morning, I think. Okay, so if we want to do global prediction, if we just want to make predictions that are good across the entire range of inputs, what might we do? Okay. Well, the kind of most obvious thing is to start by looking at the variance of your prediction across space. Yeah, we know this tells us about how good our model is, or how confident we are anyway, okay, the variance. The initial idea, Dave Mackay, was to say we're going to choose X, okay, at the point with the largest predictive variance. We're going to look at our prediction across all the space. We're going to see where the variance is biggest. Yeah, we're most uncertain there. Let's put a point there. Yep. So that seems quite sensible, right? Unfortunately, this seems to put points on the edge of the domain all the time. Yep. Because we always have big prediction on the edge of our domain because we're always, in some sense, extrapolating. Yep. So it doesn't work very well. A different idea, this by Cohn, active learning Cohn, okay, says choose X to give the largest expected reduction in predictive variance. Okay? So we look at the difference between our current kriging variance, our current GP variance, okay, at X, and the variance we would have if we were to add x into the simulator. Okay. We're going to then average this across all of space, okay, and take the expected value as well. This is saying, if we could add 1 point, what 1 point should we add in to our design to give the largest expected reduction in average variance? Okay. And this tends to work very nicely. It gives very nice properties there, designed for very nice properties, but it's incredibly expensive, right? Not only do we have to average the variance across all of space, okay, we've also got to do this optimization problem, okay, where we, for each different x, we fit a new Gaussian process with that x in, essentially, as a new training point, okay, and say, y do we expect to see if I added x in? So we've got an expectation and an integral to do across all of space each time. Okay, so that's very expensive, so you can't really do that. So there's a very nice paper put on the archive a few months ago and updated this week. Okay, the main reason I'm talking about this by Joaquin Beck and Sergio Guillas from UCL, okay, where they've got these mutual information designs. Okay. So I'm not really going to go through the details, but the punchline is that we've got a very simple criteria. Okay? We've got this criteria that you've got to maximise that has the same approximate computational cost, okay, as the simple Mackay designs. Okay? So it's about the same cost as doing it, but has the similar kind of properties for these more complex designs. So these mutual information designs say, okay, we're going to add one new design point to maximise the information between the GP prediction on our design set and the GP prediction on the points not in our design set. Okay? So what 1 point can we add to maximise the information between those two quantities? You go through the equations and it just works out as this simple ratio of the predictive variances, your GP prediction using the current design, and your GP prediction using all the points not in your design. Okay? And that's quite a simple thing to compute, and we can maximise that across all the space. So just to show you the results, I don't know if you can see these, but this is root mean squared error here as a function of the number of design points. Okay? And the red curve is the root mean squared error of predictions for these mice designs. And the points here are just the maximum Latin hypercube designs, okay, so the default choice. So you can see we get quite a good improvement in our accuracy by using these superior designs, okay. And in fact, in this case, we're beating the cone, the kind of those average expectation designs. Okay. But all importantly, the computational cost here is comparable, well, it's much cheaper than the more expensive thing we'd like to do. It's not prohibitively expensive to do this. This is quite a simple thing we can do to get improved predictive power at very little cost. Okay. So that's design if we want to make Gaussian processes that are good across all of space. Yep. If we want to make predictions that are good everywhere. What I said I'd talk about is how we do this for calibration. Okay, so just out of interest, who here has heard of ABC, approximate Bayesian computation? Okay, it grows every year, it's good. Okay, and has anyone heard of history matching? Yeah, okay, just the obvious people. Okay, so they're kind of the same thing, to be honest with you, just dressed up in different language and slightly different technical specifications. So this is the problem, okay? We've got a simulator where we specify parameters, theta, and initial conditions. And we've got a simulator f of theta that generates data x. Yep. We have some data d, and we want to solve the inverse problem. We want to learn about theta given our data d. Yeah, we want to go backwards. We've got models that model forwards, mechanistic models. We want to say something about the parameters. So, for example, in climate, we specify things like the solar forcing, the CO2 profiles, things about the properties of the ocean and the atmosphere, okay? And we simulate temperatures and rainfalls. Okay? We want to go backwards and say things about the parameters in this model. Yeah? So it's calibration or an inverse problem or parameter estimation or model fitting or whatever you want to call it. Okay? It's that. So there's two kind of approaches here. The only one I'm going to talk about now, I think, is this probabilistic approach, so the Bayesian approach, if you like. This is dead straightforward. We've got some prior distribution of our parameter. We've got some likelihood function that tells us the probability of the data given our parameter. Okay? We just want to estimate the posterior distribution of our parameters. Okay? That's all we want to do, this posterior calibration. So, one simple way of doing this are these ABC algorithms, or approximate Bayesian computation algorithms, that have come to light in the last 15, 20 years. Okay? So, people argue about what the first ABC paper was. For a long time, we thought it was this Simon Tavare and Peter Donnelly paper and David Boulding in 1999. Okay? But then someone discovered something in 1994 that was a bit like ABC, and then someone discovered another one in 1984 by Peter Diggle that was a lot like ABC, and then Don Rubin said, I did this in 1979, and so on. So it's such a basic idea that the idea's been around for a long time, and pretty much every community has an idea that is like ABC. So what are ABC algorithms? They're Monte Carlo methods for calibrating simulators. And the key thing to know here is that they don't require explicit knowledge of the likelihood function. And all inference is done using simulation instead. Okay? So we don't need to be able to compute anything, we just need to be able to simulate. And for this reason, they're incredibly popular with biologists. Yep, because they don't need a statistician to do all their MCMC for them. Okay? They just need to be able to code up their biological model on a computer. So long as you can forward simulate, model, you're fine. ABC will then do the rest for you. They're also very parallelizable and very simple and so on, and they can nearly always be applied. So what's the basic thing? Okay? This is a basic algorithm. Remember, what we're trying to do is sample from the posterior distribution of the parameter, given the data. So this is a basic algorithm. You start by just picking a parameter from your prior. You simulate some data from the model, and then you just accept the parameter if your simulation is close to your design, your data points. Okay? So you simulate, is it close? If it is, you keep the value of theta. If it's not close, you just throw it away. That's it. Yeah. So it's kind of like an intuitive thing you might do anyway. And this is what I mean, it's been around for a long time, and every community has something that looks like ABC. Yeah.
Are we assuming that all the data are coming from the same initial parameter configuration?
You mean the observed data?
Yeah.
That would be the underlying assumption, yeah. You're assuming that there is a true model, that your model is a good model, and that there's just one parameter that explains everything, yeah. Which is almost certainly a bad assumption, right? But it's kind of the standard parameter estimation thing to assume there is one true parameter. And so that assumption is here as well, yeah. And these work in the following sense, right? If epsilon's infinity here, we're always going to accept. Epsilon measures how close D and X are. So if epsilon's infinity, it says always accept, and we don't learn, we just get the prior back again. Yeah, we learn nothing. Okay. If epsilon's 0, we're only going to accept if X and D match. Okay. And then it's very easy to show that you get the exact posterior in this case, the exact posterior. So epsilon kind of controls how accurate the algorithm is. Very small epsilon, we get very accurate results, but we're going to have to simulate for a very long time to get close matches. Big epsilon, very poor accuracy, but very cheap to compute. Okay. Yes, Nando.
Can I ask you a question about this? It's
Yeah.
sort of methodological. You probably have been asked this before. I want X to be close to D, or
Yeah.
some statistic of X to be close
Yeah.
to D. But ultimately, I would want that statistic to be the sufficient statistic, so we jump back to theta.
Yeah. So what we're assuming here is that the likelihood function's unknown. Okay. So just to explain to everyone else, what we normally do here is we summarise the data with some summary that projects X and D onto a lower dimensional space. Maybe we take the mean and variance, say, or something like this. Okay. If the summary we use is sufficient, the statistic, in the statistical sense, we're not throwing away any information by doing that. But because we only do this for complex models where we don't know the likelihood function, we can never say if a statistic's sufficient or not. Okay? So it's impossible to say if you've got a sufficient statistic. So you're losing information in various places. You're losing it whenever you do this epsilon. You're losing it whenever you summarise. And it's a trade-off.
Yeah, but my question is, theta is a good statistic.
Theta is a...
Good statistic for x. Because we're simulating x given...
Okay. So
what I'm wondering if this is not a bit of a recursive way of thinking.
I'm not sure I get your question.
You need to project x and d to a space where the distance is meaningful,
Mm-hmm.
and so that somehow has to summarize what's important
Yep.
about the data. But at the same time, theta is also a good summary of the data, because given theta you can generate data.
Mm-hmm.
So we have two statistics here. And then the question is whether they have to be the same.
The problem with doing it with the actual parameter, and I understand what you're saying, I think, is that you can't do that inversion. You can't go from D to what the parameter would be. Okay? So this idea of indirect inference that is used in econometrics, that's right. So you'd fit a simple model to X and a simple model to D, find a parameter for X, a parameter for D, and then you'd use that in the sense that you said it. But we can't use the model parameter, theta, because we don't know what it would be for D. Well, that's the problem we're trying to solve. Does that kind of answer what you're asking? Okay. So to understand what's happening in pictures here, okay, we've got theta, our inputs, and the output's D. Okay, we just do a bunch of simulations. We pick a random theta, we simulate a random D. Okay, and then we suppose we've got our data. So here there's a red line at D equals 2. Okay, that's this red line here. Okay, and ABC just says draw a window or a ball around your data. Okay, and keep anything that's within that ball as a good sample. Take all the thetas that are red in here and draw a histogram. That's essentially all ABC is doing. Okay? Drawing a line through here, drawing a histogram. Okay. So you can see how the accuracy is going to prove. Epsilon's 10 here, so we've got quite a big ball around the data, or quite a big interval window around the data. As it decreases, we squeeze in, and the approximation, the red line, gets ever closer to the black line in here. Okay, so we get a narrow window. And the Bayesian exact answer would be if we could take an infinitesimal slice through here. That would be the likelihood calculation. Okay, so that's all we're doing. Okay, so getting back to Gaussian processes, the big question is, how can we do this for expensive models? Yep. ABC has become very popular in genetics, epidemiology, ecology, genetics, areas like this, because their models are very cheap. They can afford to do millions of simulations. You can imagine to do this in high dimensions, you're going to have to run your simulator many millions of times. Okay? But what do we do if we have a more complex model? Okay? A cancer tumor model, for example, that might take a few minutes to run. Yep. Or whatever your model is. Okay? If it doesn't run in a fraction of a second, you're not going to be able to apply ABC as it is. What can we do instead? Well, one thing we can try and do is try and overcome some of the limitations of Monte Carlo methods. So these are limitations in a good sense, in the sense that these guarantee Monte Carlo work, but they're bad in the sense that they're costly. So let me explain what they are. Okay. The first thing is that Monte Carlo generally doesn't exploit known properties of the likelihood function, such as continuity. So if you knew your likelihood function was continuous, your MCMC sampler or particle filter won't exploit that. Okay? You'll have to learn that fact, essentially, by repeated sampling. The other thing is they sample naively. Okay? They don't learn from previous simulations. If you're doing an MCMC sampler, okay, you're wandering around space randomly, you'll go back to the same point multiple times, even though you've ruled it out. Okay? As a bad point. So these are nice properties. Okay, it means that we never go wrong. You've got asymptotic guarantees of success. Monte Carlo methods, but they're bad in that they're costly. There's information that we have that we could perhaps use to improve things. Okay, so what we're going to try and do, I've got too many slides here, what we're going to try and do is build a Gaussian process approximation of the likelihood function. Okay. So ABC allows us to estimate, it doesn't really matter what it is, it allows us to estimate something that we treat as a likelihood function. Okay? So by doing repeated simulation, we can get some quantity that tells us how good the data is. Okay? And we're going to try and fit a Gaussian process model to these things to try and speed up our ABC. Okay. So I'm going to show you pictures, I think, here. So I've got some prototypical examples. There's some Ricker model. Okay. So this is just some model from ecology that is perverse and can be difficult to fit. Okay. So we've just got 3 simple parameters, okay, and we generate this time series of noisy data, okay, and we're going to try and estimate these parameters from these data. Okay. So what we can start by doing is just doing a large number of runs of our simulator. So I've got 3 parameters here, an R, a phi, and a sigma. Okay, so I've got all the 2D projections, and we're just going to put a simple space-filling design down to and run the simulator at each of these points. Okay. We're going to then estimate the log likelihood at each of the values in here, yeah, by doing a number of simulations, and try fitting a Gaussian process model to them. Okay. So it's going to be very noisy to begin with, because to estimate the log likelihood here, these are highly stochastic models, so you have to do a large number of runs to get a good estimate. Okay, so we're going to have to do it a number of times. Okay. We're going to try and get a crude estimate of the log likelihood, and we're going to try and rule out some bits of space as really bad, as really terrible. Okay? So it doesn't really matter what's happening here. We've got the black line, some sort of truth, or an estimated truth, which I'm cheating. I've just put on for the purpose of the illustration. The red is kind of our estimate of it, and we're just going to say if the log likelihood's too small, we're going to rule bits out as implausible. Okay. Do some more design points to the good bits of the space. Fit a better model again, another Gaussian process model, rule bits out, and we're going to go round and round this kind of loop like this. Okay? So what we find is what we're doing here is we're modeling the log likelihood, and we're introducing these waves that occur in history matching a lot. Okay? So we're going to rule some bits out, of some parts of space out as implausible, do some more simulation, build another Gaussian process model, do some more simulation, and keep bootstrapping the way up like this. Okay? So what we find if we do this, we can reproduce the results from an MCMC sampler very cheaply. Okay? So this is from Simon Wood had a paper in Nature in 2010 where he managed to get this very simple version of ABC without citing ABC anywhere in it as a pure methodological paper in Nature. Anyway, we were able to reproduce his results at a fraction of the cost by modelling this log likelihood function. Okay, so I think here he used say 10 to the 5 times 500 simulator runs. We're using 2 orders of magnitude fewer to get exactly the same thing. Okay, just by inserting a Gaussian process estimate into our MCMC sampler. Okay, what time is it? I feel like I've been talking forever. What time is it?
45.
Okay, good. I have been talking forever, of course. I've just come from physics. Okay, so this is the new bit of this talk. Okay, so this is the design bit. How do we do design if what we want to do is calibration? So this is back to Bayesian optimization here. What we are doing is classification into points as good points or bad points. Okay? We want to say for each theta in our design space whether it is plausible or implausible. This is just our set of good points and bad points. Okay? We want to be able to say what's the probability that theta is a good point. Yeah? So we've got a GP model of this surface, and that enables us to produce this probability, okay, P theta. As we've already said, design is key here, so how can we pick good design points? Okay. So I've already talked about these points. So we're going to build up a sequential design using this classification surface, and so we need to think of what would be a good acquisition rule, a good criterion to try and minimize our uncertainty about the classification. So the first idea is to try and use this idea of use entropy. Okay, so this surface is a probability across all our input space. So what is we've got an entropy at each theta, which tells us how uncertain we are about whether theta is a good point or a bad point. So the first idea, this is my idea, it doesn't work, okay, and then James showed how to improve it. The first idea is to pick a point where we are most uncertain, where the entropy is highest. Okay. So we're back to the notebook here. So we've got here, what have I got? we've got the GP mean here. The truth is in red, okay? And we're trying to find where the red curve passes through these green points. Okay, so this is our data up here. We want to find everywhere where the red curve goes through the green points. Okay? And I start off, I've just got one simulator run here, down here. Okay? So it's like Bayesian optimization here. Where should we put the next point to do this? Okay? To best learn where the red curve crosses the green curve. So if we look at the entropy surface, this tells us this is a function of how uncertain we are. So this is this red curve here, and this is our probability of our classification surface. The probability that f of theta lies within these green points. Okay? So if we put a point at a maximum entropy, we could go along, okay? And we update the model, so we put a single new point here. Okay? So our GP model improves, so now our GP mean now goes through the data up here. Okay? So we have the uncertainty shrinks down here, and we can ask the same question again. Where is the entropy? Yes?
Could you just guide me? I don't really see the
Sorry.
what those lines mean. If you could just say.
Yeah, no, I'm sorry. So the dashed red line here is truth. Yep. The green line's the data. Okay. The blue line is the GP prediction. Okay. The red line then is the entropy that we're left with. Okay, so we're going to put the point to maximum entropy. Okay, and we keep going down this like we saw for the designs earlier, and we put another point here because we're very uncertain here. We know the probability is close. We know there should be a point around here, but the probability is close to a half. Okay, so that's maximum entropy. Okay, we put another point. This is the next iteration. We have another point here. If we go along a little bit, we see this doesn't work because all we're doing is spending time resolving this point here. Okay, so we've learnt very nicely that there's probability 1 of a match in this little region here, probability 0 either side. Okay, and all we're doing is sharply defining this boundary, but we're completely ignoring everything over here. Okay, so this criteria is no good because it just makes us concentrate on defining the edges. Okay, and we can see we can keep going along for lots of iterations. It doesn't really improve or anything. So like we saw before with this active learning Mackay suggestion, okay, was that we spend too long resolving points at the edge of the classification region. We don't explore enough. Okay, so here's a better idea. This is James's idea, and it turns out it had been published before by Chevalier and people. Okay. So perhaps we can look at the average entropy of the classification surface instead. Okay. And then choose our next design point, theta n plus 1, to minimize the expected average entropy. Okay. So this is an integral of the entropy across the entire domain. Okay. And we're going to choose theta n plus 1 to minimize the expected average entropy if I was to add a new design point in here. If I can add one more design point, what do I expect my Gaussian process would look like? What would the expected entropy be? What's the average of it? Okay. So that's a very expensive calculation we couldn't do. And this works nicely. Okay, so again, dashed line's truth, green line's data, blue line is GP. Okay. So now what we're maximizing, we're minimizing the expected average entropy if we were to add a new point. That's the black line at the top. Okay, so if I just flick through what happens here, so we start by adding a point up here. Okay. We resolve a little bit, so we learn that there's probably a match in here, but then we put another point in here, and we go along a little bit, so we've resolved that there's a match in here. Okay? But now we start to explore. Rather than figuring out what happened at the edges, we go ahead a little bit, and try and resolve all the peaks. Okay? So this seems like a good criterion for doing the optimization here. Okay? If we keep going along, after just a small number of points, we're able to find all the matches, and now the process will start sharpening up these matches, okay, once it's explored sufficiently. So it's got the right kind of trade-off, we think, between exploration and sharpening up your picture. Okay. So how do we do this? So this is where the Bayesian optimization comes in. Okay. So we want to find the theta which minimizes our expected average entropy. Okay? So even for 3D problems, this becomes too difficult. Okay? So what we can do now is build a Gaussian process to do the Bayesian optimization. So we've got a Gaussian process of a simulator, okay? And then we've got an entropy across there. Now we're going to use another Gaussian process to try and minimize that. Okay? So that's not too convoluted. Okay. So this is what we're going to try and learn. So this is just a realization from a GP, and I just want to try and learn this bit in here, which I'm going to say is the good region. Okay. So essentially what we start by, this is our picture over here where we've got our estimate of the underlying surface. Okay, so I've got a few data points, okay, and the contours are our estimate of the underlying surface, okay, and the shading is our estimate of the probability that we have a match to the data. Okay. We can then look at the expected average entropy surface. Okay, this is a cheating plot. Okay, I've only created this for purpose of illustration. But what we do, we randomly sample this in a small number of locations, build a Gaussian process model of this, use the Bayesian optimization technique, so Javier software from this morning, okay, to find the point that minimizes this surface, and then add a new point in up here. Okay. So we've added a new point down here, so we start to resolve this coloring down here, the shading a little bit. And these are the diagnostics that GPyOpt spits out, or used to spit out. Okay. And this seems to work really well. After just a very small number of iterations, you can see we've quite sharply defined the points, the shape of this surface. And the nature of this criterion is that it tends to put points along the edge of the interesting region. And you can see that we're doing this. Oh, and James made me promise to play his YouTube video, which I don't think I can. Maybe we can. Oh, it's had 15 views. That's the number of times I've talked about it. So this is in action, basically. So we've got a GP we're fitting by doing another GP of the underlying surface. Okay. And we're using Bayesian optimization to optimize that. Okay. So you can, I think it's quite cool. If only because James has made it look pretty. Okay, that's enough of that. You get the idea. Okay. You can tell James I played it. It wasn't wasted effort. Okay, so we can do this for climate simulators, and we can get big savings in how much computation we have to do. Okay. So this is actually a toy climate problem. It's cheap enough that I can do it. I did 1,000 simulations here to get the truth using a history matching approach. Okay, so this is the truth we're trying to do. Okay, and this is what happens if we just use a maximum Latin hypercube with 10 runs. Oh, that's 10 runs. Okay, this is a maximum Latin hypercube with 30 runs. That looks pretty good. Okay, but you can see with these entropy-based designs, even after just 10 runs here, we're getting a very good approximation to this, okay, which is far better than this, okay, and is almost as good as the 30 runs. So you can get a big saving in how much computation you need to do. Okay, I know I've rambled on lots of different topics, but that was the brief. Okay, so just to say, basically, that Gaussian processes have become a very important tool in statistics for analysing scientific models. Yep. All kinds of scientists now are using Gaussian processes to help them analyse their engineering model, their financial model, whatever it is. Okay? And I'm hoping that with this we're going to also be able to get into the biological models that are very popular, the stochastic expensive biological models that are very popular in genetics at the moment as well. Okay? The only other point really is that design is really important if you want to minimize the amount of computation you have to do. If you really have an expensive simulator, you can make big savings by thinking carefully in advance of doing any simulation. Okay, that's all I'm going to say, I think. Thank you. your dimensions varying.
Yeah, so a lot of physical simulations, you've not got a set number of parameters you're putting into them. Have you done anything?
No, I haven't. No, I don't. I haven't thought about that before. I'm not going to try and do now. No, but interesting.
So often in design and inverse problems, you have expensive simulators, but you could inject information of lower fidelity. For example, run the same simulator at lower resolution.
Yes.
Could you incorporate this data maybe in the context of multi-output techniques?
Yeah, so people have looked at this. So the idea there, so say with the oil, the fluid flow problem, you can run your simulator at various levels of resolution, right? So you can afford to do the low resolution model many times. So you start off by building a cheap emulator of that, okay, and use that as a prior for the next level of complexity, and use that for the prior of the next level of complexity. So yeah, so people do that. So this is called multi-level emulation, and it's very much like the multi-level Monte Carlo that you've probably seen a lot of in the past few years. Okay. So yeah, no, people have definitely thought about that. I've never done it, but people have. Yeah. Yep.
So it's a stupid question because I got a bit lost. But when you reduce the space of inputs,
Mm-hmm.
you might end up with very disconnected sets, and you want to sample again from those sets to run your emulator again. But then is that the sampling that you're doing with entropy-based designs, or is that something done differently? Or how can you guarantee that this is a good design so that you can run your emulator again?
So ask that question again. So you want to sample from the good region?
Yeah, when you're doing the history matching,
Mm-hmm.
every way you discard sets of,
Yep.
of the input space. So and then you want to run your Gaussian process again
Mm-hmm.
with values pertaining only to those new regions.
Yep.
So you have to sample again from those new regions.
Mm-hmm.
Are these the entropy-based designs that live in those new regions, or how are you sampling from those new sets?
So I'm a bit confused. You mean you want to put more points into the good regions?
Yeah.
Okay. So yeah, that'd be the entropy-based thing. So
Right.
you have some criteria, maybe multiple criteria for the different levels. Okay, and you would you'd try and optimize your next point to minimize those criteria.
But you
Yeah.
don't discard the points that you have.
No, you don't discard the points you had before. No, certainly not. No, they're useful points. Yeah.
Other questions? If you don't ask another question, the school will end.
I think that's the idea.
Oh, it's going to end on time, bang on time as well.
Oh.
So if we could just thank Rich again for a really great talk. Of course, that was a partial lie because there's still a social event for half of you tonight. So is there a plan of where to